Hello everyone, how are you? I hope you're enjoying your industrial carbon section. So now we'll move on to a very important industrial carbon material. This is known as carbon black. So carbon black is actually something that has been industrially manufactured for over 50 years, and we already have well-defined, optimized, scaled-up processes for the manufacture of carbon black. This material is very important because this is used for reinforcement of rubber in the case of tire industry. Okay, so you can imagine that tires have been very important in the last 50 years. There has been so much development in the automobile industry. There has also been, you often hear that, you have now more advanced tires which last longer and so on, all thanks to carbon black. So in fact, it is the properties of carbon black that have been improved, and also of course of the rubbers, but this is the material which is used for the reinforcement. Of course, there are many other applications as well. You can reinforce other polymers and you can make them electrically conductive. The standard properties of graphitic carbon materials, of course, they are also valid for carbon black. Okay, so what is the definition of carbon black? Well, it is a turbostratic colloidal carbon. And these are particles, so it is a particulate material. Okay, so there are multiple things here. Turbostratic, you understand, turbostratic is basically nothing but if you have these graphene like sheets in a material, any carbon material, and they are randomly rotated on top of each other rather than in the ABABA fashion, then you call it a turbostratic material. Now, often the materials that have a strong curvature, curved carbon structures, they tend to be turbostratic. Because it's difficult for them to have these flat geometries and ABABA, graphite like crystalline order. So that is something you understand. This is also a material with short range order. Okay, so you don't have, of course, that is when you have the particles. Now, what do we mean by the colloidal carbon materials? So whenever you think of a colloid, what comes to your mind is a suspension. So if you have these particles, you put them inside a solvent, then what you're going to get is a suspension. Okay, so this is basically what we have here, but these are carbon particles. So we are still talking about solid carbon particles, not the solution. However, if you did make a solution or you tried to dissolve it, they will not get dissolved. Carbon is already, it does not get dissolved easily. But the point is that the particles are not so large that they will settle. So you will have sort of a suspension. These are the colloidal carbon particles. So here is an image. This is a transmission electron micrograph of carbon black. You see, this is like a bunch. This is a cluster of nanoscale particles. So when I say the particle size should be 1 micrometer or smaller than 1 micrometer, I'm talking about the entire bunch, the entire cluster. And these are called particles, but they are not necessarily spherical. We rather take an equivalent sphere when we calculate the diameter of these particles, for example. These are actually very small nanoscale carbon particles, and they are fused together. They form a bunch or a cluster because that provides them a more stable geometry, and that is why we have these clusters. The cluster size in its longest dimension should be approximately of the 1 micrometer range, so it's not exactly 1 micrometer. Often the individual particles are in the 10 to 15 nanometer range, and the bunches, they are typically slightly above 1 micrometer, so 1050 nanometer, for example, but this is acceptable approximately, so they should be in the 1 micrometer range. Okay, so this is how these bunches are known as carbon black particles. So now let's talk a little more about the colloidal systems. So what is most important in a colloidal system is the size of the particle. If the particle is too large, then it will settle. If it is too small, then you don't call it a colloidal system. So we are going to compare the colloidal systems with both small molecules and the macro scale systems, particles. Okay, so in this case, in the case of colloidal particles, you need to have the size range within 1 nanometer to 1 micrometer. So this is the definition. But if we compare it with two things, first we compare it with the small molecules, and two, we compare it with the microscale particles. So the first comparison, in terms of when we compare it with small molecules, well, small molecules will have, if you put them inside a medium, they will have a much larger contact area. But compared to small molecules, then you have a smaller contact area, although it is also relatively very large. But compared to small molecules, if each individual nanoparticle, in fact, from the colloidal particle also, if every nanoparticle was, away from each other, it was separated, then you will have a much larger contact area, surface area. So that is how they differ from the small molecules. Okay. Now, why does this happen? Because the enthalpy of interaction with is smaller compared to the smaller molecules, and also the entropy, which is due to the translation. So what is entropy of any material inside a solution? How randomly your particles can move, how fast they can move, how much they can go away from each other. So these are the translational motions of your molecules that determine the entropy of the entire overall system. So for these particles, compared to the small molecules, the entropy and enthalpy both are smaller, and that is how you will say that okay, these are there's less contact. Okay. Now also there's one more important thing when it comes to, so we are talking about these colloidal particles, but they have, you can see there are a lot of small particles all together, they're fused together, right? Can we have different organizations of these particles? So when we are talking about enthalpy and entropy, then probably it's easier for you to understand that if you just switch the positions of these nanoscale particles inside your carbon black particle, still you're probably going to have the pretty much the same enthalpy and entropy, because as long as the overall dimensions are in this 1 micrometer range, you're not going to see much change in the behavior of your particles. So the answer is yes, you can have various organizations of these nanoscale particles, and the shape of this cluster is not well defined. So it is like a cluster, or it's like a bunch of grapes. So the bunch of grapes can have slightly different shapes, one bunch from another, but still the overall energy, and that is the reason that we call them, we consider these individual 1 micrometer scale particles as our individual particles, because these particles are pretty much of the same surface energy, and they particularly have the same properties, even if there is a small variation in terms of the organization of particles within the system. Okay, so that is one thing that that differentiates it with small molecules. Now, when it comes to comparison with larger or macro scale particles, then we don't call them molecules, we call them particles. Then in that case, of course, the most important difference is that you have the Brownian motion. Which you will, so if you have fluid as a medium, then you will have Brownian motion in the case of carbon black particles, or colloidal, any colloidal particle, which you do not have in the case of large scale particles, because they typically tend to settle down. Now when we talk about the Brownian motion, Brownian motion is basically something that opposes all the inter-particle forces. Also, it opposes the gravitational forces. And that is why here the low density is also very important. The light weight of the carbon is also very important. And this entire material, in fact, it's also called a fluffy carbon material, because this is like a very fluffy, spongy material altogether, even individual nanoparticles, because they do not have a very, they have a short range order, only a short range order. So these are very small turbostratic crystallites, which may also contain a lot of defects, which may also contain some impurities, and their weight is also, because of the individual particle also has a very low weight, and of course when you see a cluster, then you can see that there is a lot of empty space, so to say, in that cluster. So altogether, you have this kind of Brownian motion because of multiple factors, because these particles, they are able to oppose the gravitation, the van der Waals forces, other interactive forces between, between two particles. Cluster of colloidal particle, as I already mentioned, that it looks like, something like a bunch of grapes. And that is why it is also sometimes called aciniform carbon. Now, the word acinus means grapes. I think it comes from Latin. So, because these particles look like a bunch of grapes, so this is also another term that you will hear, aciniform carbon, when it comes to carbon black. And here is a picture where I have shown the what is the proposed microstructure. So the second image here you can see that there are these very small short range orders, so small crystallites, but these are not again well defined crystallites. So you will get only a broad peak if you perform diffraction studies. So however, you do have, so this material is also composed of these hexagonal carbon sheets, but these hexagonal carbon sheets tend to have defects, and they tend to have very small range order. So they are just like fused together, and this is also one reason that the density of the particles even at its microstructural level is very low. Okay, so yeah, here I have also mentioned this review article. Maybe you could go through that and understand more about this material. Okay, another very important thing that you should understand about carbon black is that carbon black is not soot. So in the beginning also I mentioned that not everything that is black and carbon is called carbon black. There is another term which is called black carbons, which is very confusing. So sometimes when you get these soot is what comes out of your car exhaust, that is diesel soot or petrol soot, or whatever comes out of the candle, that's also soot. So all of these materials are unburnt carbon materials, and your carbon black also contains unburnt carbon particles, and that is why often soot and carbon black are confused. People think that soot is carbon black. That is not the case. There have been several articles published and a lot of studies that have been done where a comparison of soot and carbon black is made, and then you can understand what is the difference. So this is what we are going to discuss. One important thing about carbon black. So before we talk about the manufacturing that we'll do probably in the next class, the point is that this carbon material is interesting and also different from other carbon materials in the sense that it contains some impurities. It does contain hydrogen, and it may even contain some tar, like small fractions of tars or moisture, and these impurities are acceptable. What is interesting about this material, it's not fabricated, it's not manufactured using the pyrolysis process, but rather a combination of pyrolysis and combustion. So this is probably the only large-scale carbon material that you will hear that is actually prepared in the presence of oxygen. Okay, so you're essentially performing a combustion, but in a very controlled environment, and that is important to mention here because when we have soot, then the conditions are not controlled. So what comes out of your car exhaust, you know that these are unburnt carbon particles. We also discussed them in the context of environmental pollution, that these exhaust gases contain not just black but also brown carbon. And that brown carbon is nothing but carbon that contains a lot of tar. And these are being formed in a very, there's no control over that process. Okay, but in the case of carbon black, you already saw that we have these grape-like carbon particle structures and so on, and these are being fabricated under highly controlled environment. Despite the fact that you have oxygen in the system, the quantity of oxygen in fact is optimized, and then it is the combustion is performed in a highly controlled fashion, and the particles of course need to have a very well-defined size and well-defined geometry, and even the smaller particles, the nanoparticles that form these clusters, their size is also well-defined. That is not the case with soot. So let's discuss what is soot and what is carbon black. Okay, so I mentioned that both carbon black and soot contains stars. So even if carbon black contains tar, then how can you say that it is different from soot? Well, number one, the total C by H ratio. So the ratio of carbon to hydrogen in the case of carbon black is much higher. This is what is known as the elemental carbon ratio. So that is much higher in the case of carbon black. Another important thing is that in the case of soot, you can often have larger droplets of tars. So when you're burning diesel, then you can actually, there is diesel being sprayed, and then it is getting mixed with the oxygen, and then it is burning. Basically, some particles remain unburned, some even the tar itself goes out, but you may actually end up getting larger droplets of tar. So large means it can also be 5 micrometers. So you know that in the case of carbon black, the entire particle size is 1 micrometer. Now, if there is a 5 micrometer size tar ball, that is going out, even if it is partially burnt. That is what happens in the case of soot. So you do not have any control over size. Also, you do not have any control over the fraction of tar. Often you have a much higher fraction of tar in the case of soot. Okay. Now, there may be not just tars, but also sometimes some sort of resins in the case of your soot. So that will depend on what kind of soot it is. Not diesel soot, but candle soot or other. So you will also have these large hydrocarbon resin-like molecules that are also present. That is definitely not the case with carbon black. Okay, so carbon black looks something like this. We already saw the TEM image, and the soot might look something like this. So as I said, you may have brown carbon particles which basically contain tar, and you can have relatively larger amounts of tar. You can also have some inorganic materials mixed. So this is another difference. In the case of carbon black, because you're using a hydrocarbon source, so we are also performing processes similar to pyrolysis, but in just the fact is that it's not pyrolysis, because there is a combustion going on as well, because there is oxygen present in the system. But we are sort of optimizing how much of the process should be pyrolytic and how much of it should be combustive. But that is not the case with soot. So you will often have these kind of particles. Now, you may think that these are also colloidal particle, and it becomes confusing because, as I already mentioned, people call soots and all of these impurity containing forms of carbon black carbon, and so black carbon is sometimes confused with carbon black. Anyway, the point is that if you carefully observe, if you do the particle size analysis, then you will realize that, or also when you perform elemental analysis, you will know that carbon blacks are quite different from the soot. However, soot can be heat treated further to get more purity. So the process that is used for making carbon black is typically the temperature of that process is between 1300 and 1500 degrees centigrade. Okay, so if you take your soot particles and anneal them out, basically get rid of your too much tar that you had in the soot, in that case you can potentially get a material which is similar to carbon black, but you may still not be able to get carbon black because you may not be able to get these perfect grape-like particles. Okay, so well, yeah, one more thing is that please don't confuse soots and don't use them for all the applications, because they can be carcinogenic. So they may cause cancer. They basically have a lot of safety issues. In fact, that is why we are studying all this environmental pollution and everything, because these brown carbon particles and also some of the black carbon particles, they have carcinogenic effects. So soots are therefore, but that is not the case with carbon black. So soots contain various hydrocarbons. They contain naphthalene. They can contain various polynuclear aromatics. So because of the presence of all of these non-carbon materials or hydrocarbons, you have carcinogenicity in the case of soots. So yeah, as I said, you can heat treat your soot and potentially get something which has a high carbon content, but it may still not be carbon black, because the density of those particles can be different. The size of those particles can be different. Carbon black, when you have these bunches of nanoparticles, what does that mean? That means that first you're getting these nanoscale particles, then they are fusing together. So this is a bottom-up process. You will not get the same kind of material when you heat treat the soot, or the soot should have been also formed with the nanoscale particles. In that case, heat treatment might lead to carbon black production. In fact, sometimes in some industrial processes, the first initial stages of production, when you perform the combustion, at that time, whatever material is formed, people call them soot also. So that is another confusion in this regard, but you understand that what is the difference. Okay. Yeah, so this is coming to a completely different topic. I told you before that India is one of the largest producers of carbon black. What is also interesting is that the history of carbon black has a lot to do with India, because one of the first inks that were developed in the world. So in India, we don't know when did printing or the large scale writing started. But we definitely know that India did produce inks even 3000 years ago. And approximately 3,000 years ago, we actually had well-defined carbon black production in the country, and those carbon blacks were used as pigments for these inks, and those inks were actually supplied all over the world. They were even called Indian inks. So carbon black has its history, definitely involves India. Okay. Now, the applications, I already mentioned that reinforcement of rubber is the most important application, and that is why we have the large scale production. Okay, but other than that, of course, pigment in inks. Even today, a lot of printing inks contain the black color inks are often based on carbon black. And then you can also reinforce other plastics, and you can you can make coatings. Many plastics or polymers, for example, PVC, polyvinyl chloride, is often reinforced with carbon black. And once you, so also for research purposes, if you add carbon black particles into certain polymer, of course, the mechanical strength increases. So this can be used in composite materials, but also the electrical conductivity increases. So for that purpose also, you have to optimize the fraction of carbon black in your polymer, but for multiple applications, these the particles are used. Okay, so when we reinforce the rubber using carbon black, then what is the mechanism of this reinforcement? Well, there are two things, or at least these are two theories. That the first one is that there is a filler network. So this is fillers. We will talk about composites in detail. You always have a matrix phase and a filler phase or additive phase. So carbon black is used as a filler. So you will basically, this filler network provides stability and mechanical strength to the material, and also the interaction of the matrix phase and the filler phase provides mechanical strength to the overall system. In fact, there have been several studies where people have figured out what's the mechanism, because carbon surface, you see this material is a very high surface area material. Surface area is the most important thing when it comes to carbon black, and also it's light weight, and because it is fabricated in the presence of oxygen, you can imagine that you will also have certain surface functional groups which will make it hydrophilic. Also, you may have certain radicals present on the surface, and these radicals can actually enhance the polymerization or the rate of polymerization in a polymer. Okay, so this is also another mechanism by which on the surface of the carbon black particles there is an improved rate of polymerization of your matrix phase. So because of these, this is how you basically get your rubbers in, with better properties, better mechanical properties. Okay. So here I have mentioned one article. There are many articles where comparison of soot and carbon black is made, but this is one of the older articles which you can read, and you can actually see both at industrial scale and also at research scale how soot and carbon blacks differ from each other.